Hello everyone, I'm Salman Sadiq Shuvo, a PhD student in University of South Florida. I'm going to present my paper on predictive maintenance for increasing EV charging load in distribution power system. My supervisor Dr. Yasin Yilmaz is my co-author, and this paper got accepted in IEEE SmartGridComm 2020. I will first introduce the problem of overloading our power system, especially the distribution transformer, through increasing EV charging load. Then I will talk about some background about how overloading expedites aging and failure in a transformer, followed by the markup decision process based setup for our model. After that, I will discuss the deep RL based optimal policy for the problem, which includes the advantage actor critic algorithm. Then I will show the simulation results of the performance of the deep RL policy in comparison with three straightforward myopic policies. Then I will conclude the paper. Electric vehicle will dominate the automobile industry in near future. Bloomberg NEF publishes EV outlook every year, and they come out with the most aggressive EV inclusion forecast. They expect 508 million EVs on the road globally by 2040. The numbers are 10 million currently as of year 2020. Oil majors have more conservative EV adoption forecast. That's kind of understandable. However, most of them have increased their long-term EV outlook at least once over the past 3 years. Even British Petroleum and OPEC both expect there to be 300 million passenger EVs on the road by 2040, which is still 30 times of the number of EVs on the road currently. Electric vehicles needs to be plugged into an electric outlet rather than refueling at a gas station. Electricity demand from all kind of EVs was 74 terawatt-hour in year 2019, which will rise to 2,331 terawatt-hour in year 2040. However, that will be only 6.8% of total global electricity in 2040. In fact, the impact of EV inclusion is more significant in peak power demand than the total energy consumption. The graph shows the average peak demand of a household with electric cars is more than double of a typical household. The existing residential distribution grid is not designed to account for EV loads. A regular home in the US has an average load of 1.2 kilowatt. At the same time, an electric car, such as the best-selling model Tesla 3, adds another 7.7 kilowatt load to the household, effectively more than doubling the peak electric demand of the home. Transformers are the principal component in electricity distribution. The customer transformer faces the most impact of EV inclusion, hence the focus of our research. Typically, these transformers, except for 1 and 2 in figure, are smaller in capacity, ranging between 10 to 100 kVA. And are fuse protected. Because of the convenience and low cost, most EV drivers do more than 80% of their charging at home. So if the households under a particular transformer adopts EV aggressively, the transformer will be overloaded soon and require replacement. The horsepower temperature of a transformer is a sufficient parameter for aging estimation. Generally, the conductor or insulation material is the hottest spot of a transformer, whose temperature cannot be measured directly. So the horsepower temperature theta H of a transformer at time n is the summation of ambient temperature theta A, top oil temperature rise over ambient theta O, and horsepower temperature rise over top oil temperature theta Z. Both theta O and theta Z only depends on loading L for any specific transformer. The graph shows aging acceleration factor FA in log scale for theta H. It means if the horsepower temperature of a transformer is 110 degrees Celsius for 1 hour, it will lose 1 hour of effective life. But if the horsepower temperature is 130 degrees Celsius, then it will lose 10 hours of life, where for horsepower 90 degrees Celsius, it will lose only 0.1 hour of effective life. IEEE recommends 20.55 years of effective life for distribution transformer. So we can calculate the effective age of a transformer by adding each hour of effective age in it accumulated through serving the load. We use variable hazard function to generate the aging related failures. The probability of transformer failure during the ith day is probability of I that depends on effective age AI of the transformer. Alpha and beta are respectively scale and shape parameter of variable distribution whose value can be modeled from existing literature. We apply Markov decision process for our problem. In our MDP model, the electrical utility company is the agent. It has m transformer in its distribution network. For a transformer, the ratio of its hourly actual load and its capacity is its loading. Initially, all the transformers are 25 kVA in capacity. It is the hourly additional load due to the inclusion of an EV at the tth time step. Effective aging is calculated as described earlier. The transformer can cause interruption cost to the utility if it fails or the fuse blows. The underloaded and young transformers made bad candidate for the change. Hence, at every time step, the agent creates a pool of B candidate transformers for same capacity replacement or upgradation to double capacity 1. So it has 2B plus 1 possible actions of doing nothing or replacing or upgrading any of the B transformers. The new transformer age will be 0. Subsequently, the age and load of all the transformers defines the state that satisfied the Markov property. Interruption cost of a transformer will be calculated at every base time step. That can be daily, hourly, or smaller time step. This will cause if the transformer fails or its fuse blows. On the other hand, agent's action cost will be calculated at MDB time step. That can be daily, weekly, or even bigger time step, necessarily greater than or equal to the base time step. The goal of the MDP agent is to minimize the discounted cumulative cost CT in T time steps. The solution lies in minimizing the expected cost by selecting the appropriate action XT. Central to this problem is the Bellman equation, where after ith iteration at time t, the agent's value function Vi is obtained from RL algorithm that looks for the best action through simulations by assessing the expected cost for each of the 2B plus 1 possible actions. CMT is the immediate cost caused by the mth transformer by serving load during time t. Since the agent's action changes the next state of the transformer, the future discounted cost through the value function of the next state Vi-1 depends on the action of the agent. The age and load are continuous and create an infinite number of possible states. Thus, we require a neural network based deep RL algorithm. The advantage actor critic algorithm, which is a policy gradient based algorithm, is suitable for continuous state space. It also employs two neural networks, actor network and predict network. The actor network, also known as the policy network, outputs probability for each action value through a softmax function. On the other hand, the critic network learns the value function for each state action pair. This is the pseudocode for our algorithm. At the beginning of an episode, transformer state is initialized. For a 50-year timeline, every day, EV inclusion to any of the transformer is generated from a binomial distribution with user-defined probability P. Aging is calculated and corresponding failure events are generated from variable distribution every day as described earlier. At the end of the year, the utility takes an action based on the policy network. At the end of an episode, actor and critic network are updated according to the advantage actor critic procedure. In our simulation setup, the neighborhood has 25 number of 25 kV distribution transformers. That serves 200 homes resided by 502 people. Residents there drive 348 petrol cars. There are three neighborhoods based on different EV penetration rate. In the low EV penetration neighborhood, all of the 348 petrol cars will be replaced by EV in 100 years. For medium and high neighborhood, those petrol cars will be replaced in 50 years and 25 years respectively. The scheduled replacement by a 25 kVA transformer causes $1,000, whereas $22,000 for upgradation to a 50 kVA. Transformer failure causes 24 hours of outage and replacement cost, $2,000 for replacement by 25 kVA or $3,000 for replacement by 50 kVA. Fuse blow costs $500 and 6 hours of outage. Failure and fuse related costs are higher as they require emergency service and get no salvage value for the failed transformer. Furthermore, they cause unexpected outages that cause the utility in terms of unserved electricity and customer dissatisfaction. We compare four policies. Failure-based policy is the ideal one, which only replaces transformer by the same capacity once it has failed. This policy does not do upgrades, thus fails to cope with EV inclusion and results in excessive fuse blow and transformer failure events. The myopic policies upgrade or replace the transformer yearly based on some predetermined thresholds on load and age. The myopic policy that prioritizes load over age performs well to reduce the number of fuse blows, but the number of transformer failure is high. The other myopic policy that prioritizes age over load performs well to reduce the number of transformer failure, however, fails to control fuse blows. Deep RL based policy performs better than any of the policies. We take the cost and outage of failure-based policy as a unit to compare the benefit of maintenance policies. Deep RL-based policy reduces 55% cost with respect to the failure-based policy, compared to the 37% and 29% cost reduction by the load priority and age priority myopic policies. Deep RL-based policy performs even better in reducing outage by avoiding 70% of the outage caused by the failure-based policy. The age priority myopic policy reduces outage by 62%, whereas the load priority one reduces by about 48%. While both myopic policies are effective in reducing the cost and power outage, the proposed deep RL-based policy clearly achieves the best performance. This work aims to guide electrical utility companies for predictive maintenance for the distribution transformers. A reinforcement learning based algorithm comes up with an optimal policy to replace only one transformer at each time step by same or higher capacity ones. A straightforward policy for the utility might be to look at age and load of a transformer for its replacement. However, the actual dynamics of cost with age and load remains unknown, and utility tends to set some threshold for replacing a transformer. Experiments exhibit superior performance of our deep RL model for maintenance cost and power outage reduction, indicating the RL algorithm better understands the correlation between cost, load, and age of a transformer. We aim to extend this work on a larger network consisting of thousands of distribution and power transformers of different ratings. Including demand-side management will make this problem more interesting. Thank you for your time.